So we wait a few seconds for everyone to come into the meeting, but I say already some hello, good morning, good afternoon. Let's give it a few more seconds. Okay, everyone. Let's start the second midterm webinar of Code for Earth 2025 edition. And my name is Atina Trakas. I'm here with my colleague Esperanza Quartero. And we're supported by Sara Bozzi and Diego Domenici from Compliant Trust IT. Yeah, and we will hear today as I said, it's the second webinar. So we had 2 weeks ago, we heard from the first 5 projects of this year's edition in Code for Earth. And this webinar, the participants will share their findings so far, where they are, state of play, and will explain how the project works. But before we go to the presenters, to the participants, let me say a few words about Code for Earth for those who are not familiar with the program. Code for Earth is a key innovation action run by ECMWF and supported by Copernicus Destination Earth, and also supported by a partner organization. And these challenges we are putting out every year are meant to identify challenges in the broader Earth science community, touching also on weather, climate, atmosphere. So we are welcoming each summer individuals and developer teams who have a different background. So if you're in earth science, computer science, or you work on artificial intelligence, machine learning, or software development, please have a look at the next edition. Maybe there is a challenge that is of interest for you and you can submit a proposal. It's all about innovation, collaboration, networking, and of course, open source software development. And those selected teams that finish their project successfully by end of August, they receive a 5,000 euro stipend. This is in very short the content of the program, how it works. And the program is divided into different phases. As I mentioned, we are putting out challenges yearly. That is usually around February. We put problem statements, challenges out to GitHub, and then we issue a call for participation, and interested people can submit a proposal by answering these challenges. Then in phase 2, we are evaluating all the submitted proposals, and the mentors of each challenge are looking into the proposals. And maybe let's jump one step back. You will find all the challenges each year on GitHub. So we have a GitHub space where you also can browse through previous editions. From the call for participation, we go to the selection or evaluation phase. And then in May, early May, we start the coding phase with the selected programs, with the selected projects. So this is where we are right now. As mentioned, we had a first midterm webinar 2 weeks ago. And I also mentioned that we work together with partner organization. And here I would like to thank our this year's supporters and challenge partners. That is NSOE, the European Network of Transmission Systems Operator for Electricity. We work closely with Forschungszentrum Jülich, the research centrum in Jülich, and another partner that has been also around last year, and we are grateful to have them again, is Helmholtz-Zentrum Herion. And the last joint challenge partner is IFAB, the International Foundation on Big Data and Artificial Intelligence for Human Development. And without further ado, I would like to hand over now to my colleague Esperanza, who will guide you through the next couple of minutes.
Thank you, Athena. This year in 2025, we have 40 mentors from ECMWF and also from our joint challenge, joint partners to working on the Code for It projects and collaborated with the teams. So we would like to take this opportunity to thank to all of them for their continuous support, help, guidance, and expertise to all the teams. You can read all the names on the screen. Thank you. Next slide, please. As Athena mentioned, on 9th of July, the first session of this midterm webinars series took place. And during this session, five projects, Code for It projects, presented their results. The first demos are introduced their projects. But if you miss it and if you're curious, we encourage you to watch the recordings. These recordings are available on our YouTube channel, but also on our website. Go to the page Midterm Webinars, you will find the link there. Next slide, please. And now on the spotlight is the time for the 5 remaining Code for It projects. We are happy to have them, all the developers here. And without any further delay, we are going to introduce the first team. The first project is AI for Quality, High Resolution Air Pollution Downscaling. This project is developing 3 AI advanced models to deliver accurate air quality insights. People or the developers behind these projects are Kevin, Marcos, Nuria, Victor, and Francisco. Please, the floor is yours. When you're ready, please introduce your project and tell us everything about it.
Perfect. Thank you, Esperanza. Just checking. Can you see my slides and hear me well? Perfect. Okay. Thank you. So, well, let's start. First of all, thank you all for coming. I'm Kevin Monsalvez, and I'm going to present the work that we have been doing for this project, AI for Air Quality, with my colleagues, Marcos, Francisco, Victor, Nuria, and me, for the 21 challenge of this year's edition Code for Air. But first of all, we wanted to thank our mentors here on the left for all their valuable feedback and all the suggestions, and in general for all the support that they have provided us. So thank you. So as I said, this is the work for the Challenge 21 that consists of applying AI techniques for performing downscaling of global air pollution fields. So this downscaling just means to departing from a map at low resolution to obtain its higher resolution counterpart. So why do we need or do we want this high resolution air pollution data? Well, among many things, because these are necessary to improve the air quality policies, right? And then to help mitigate and decrease the risk associated to these pollutants. Actually, there are already some global products, as CAMS Global, that cover the whole globe, but they have a very low resolution, and therefore they may miss some variability that are important for complex terrains like mountains or cities, right? On the other hand, we have regional models like CAMS Europe that they have a high resolution and then they can capture this variability, but they are computationally very expensive to produce, and therefore they are limited to some regions. Actually, here on the right, you can see the CAMS Global and also the CAMS Regional here for a given day, and for the very important pollutant called particulate matter smaller than 2.5 micrometers, so PM 2.5, okay? This is very important, it's the one that we are going to focus along this work. And actually, there are already traditional downscaling techniques that allow you to go from this low resolution global product to the high resolution one. However, these are either computationally very expensive, or on the other hand, they may be like usual linear interpolation, they may produce unsatisfactory results. That is why we are exploring the use of AI-based techniques to perform this downscaling, because they have been shown to produce high-quality outputs in a much faster way, and requiring a smaller computational budget. Okay, But before that, the first thing that we did was to study which data we are working with, right? These comes global and regional products. So we compute some metrics, for instance, the correlation among both, and we found already that they are two different products, and then they have differences both regionally and also seasonally. Okay, and on top of that, since the models that produce these products change over time, the correlation among them also change over time, as you can see here. Therefore, well, this is important to have in mind because this may pose some problem to train the models. However, despite these problems, we are actually finding, I would say, more or less good results, as you can see on this image. For instance, on the left-hand side, you can see the ground truth of this PN 2.5 for a given day at high resolution in this case. And on the right-hand side, you can see the prediction, the outcome of our models for the same day and for this PM 2.5 pollutant. And you can already see that we are recovering these higher concentrations for regions like north of Italy or capitals like Madrid, or this cloud here over the north of Europe, or on these cities, in these cities on the east that are also showing high emissions. So how are we arriving to these results? Well, so let me tell you a bit about the solution that we are implementing. And first, the first thing that we wanted to study is a causal inference analysis. This is sort of a rich feature selection where we are studying the causal effect relationships between the input and output variables in such a way that we want to remove the spurious correlations that arise from these variables and that may just introduce noise to the training procedure. Then we are exploring 3 AI models that I will talk about them in the next slide, but just to mention them here, we are exploring a UNet as a baseline, the swim sphere that is based on visual transformer, and a novel spatial adaptation of this Modafno model. And for the training, we are considering well, these variables that you can see here at low resolution from CAM's global forecast. So obviously PM 2.5 at low resolution, but also other wind-related and temperature-related variables, plus some high-resolution static features as orography, population, and so on. Then, as the output data, we are considering the high-resolution PM 2.5, what we want to reproduce with our models from this CAM's European forecast product. Then we are evaluating with these Fairmont metrics and some that you will see later on, and also against observations, real observations in Europe. And then we want to test how well our models are able to generalize outside Europe, so outside regions for which they have not been trained, right, like China or the States. Regarding the AI models, as I said before, we are exploring as the baseline a UNet. This is based on convolutional neural networks and is the usual architecture that is you can find in the literature when looking for
Kevin, are you there?
Sorry, we are having a thunder right now, and our research center has a quick delay, so Kevin is restoring it.
Okay.
The internet connection, sorry.
Thanks, Nuria, for telling us. Are you in the same place than Kevin?
Yes, but I'm connected through the mobile phone, not through the internet from the research center. That's why I still here.
Can you take over so far, or is...
Yeah, well, maybe then maybe what we can do, Marcos, Victor, Francisco, is that we go each one spending the slides. Okay?
Yeah.
Okay. Let me share the screen. Okay, can you see my screen?
Not yet.
Hi,
Yes.
hello. Sorry, I'm sorry. We lost the connection. I think there is a thunderstorm here and the internet just went off. Sorry so much.
Yeah, we heard.
Okay, then I give you the floor again.
Okay, let me share then. Can you see the slides again? Well, I hope so, right? Well, as I was saying, yeah, that we want to try to test how they generalize the models, okay, outside Europe. Okay, I was in the part of well, yeah, so besides the exploring the unit, we are also studying a more advanced model, let's say this swing free transformer that we chose because well, the transformer architecture is the one that underlies the current success for almost all foundational models, right? Like in text domain like ChatGPT or Llama, or also in vision domain like Dino, SAM, and many others, right? So we are taking one of the state-of-the-art transformer models for statistical downscaling and applying it for our case, okay, downscaling these pollutant concentrations. And finally, we are exploring this spatial adaptation of MODAFNO. This is a model that is based on Fourier neural operators that was later adapted to the visual domain by combining with the visual transformer architecture, but in such a way that it is much more efficient than the traditional transformers. And in our case, we are taking this MODAFNO model and we are implementing a novel spatial conditioning, okay, such that we can condition the network via these high resolution features as orography or population density. So one of the main results that we are obtaining is this comparison among the three AI models and also a linear interpolation traditional method, right, from CANS Global. So well, we are comparing with all these metrics here, and we are already finding that the swing free transformer is the one obtaining the best results for almost all metrics, but is the one requiring the largest computational budget, okay? These results are followed closely by the spatial MODAFNO, that is the one requiring the smallest computational budget in this case. And also the unit, the baseline, is able to compete against these models for some particular metrics, okay? But in general, the three AI models are able to beat the linear interpolation. So now focusing on the swing free transformer, that is the one giving the best results. Here on the right, you can see the difference between the output and of the model and the ground truth for a given day of this PN 2.5. And concretely for these 1, 2, and 3 pixels, we saw here on the left the historical record for the input, the target, and the output of our models. And you can see that the target and the output, well, they are very close to each other, so meaning that we are getting more or less good results. Now we wanted also to do some interpretability analysis over this swing free transformer, and well, we first assessed the importance that the model plays to some of the features, the input variables, to produce the outcome, right? So we saw, as one may expect, that the PN 2.5 at the low resolution is the one giving well, the most importance, and followed by some meteorological variables, like here about the temperature and also the orography here. And on the right, you can see where the model is placing also more importance, spatially speaking. So the region that is paying more attention to produce the outcome, right? And as one may expect as well, it gives more importance to places with higher concentrations. And finally, as I said before, we wanted to do some causal inference analysis to remove the spurious correlations and help the training. And well, even though this is still an ongoing work and we have yet, well, more to do, we wanted to present some preliminary results using this PCMCI method that, summarizing it, it study how the correlation between pairs of variables are modified when a third variable is also changed, okay? And this way, one can extract the different causal links to the PN 2.5. Then removing unrealistic contemporaneous links and just focusing on past time steps, we find that the drivers of the PN 2.5 at high resolution are the V and U wind components and the dew point temperature. And just finishing, as future steps, we have to yet finish the development of the AI models. We have to also evaluate against observations, as I said before, and we would like to test how these models are able to extrapolate to regions outside Europe. And finally, regarding the causal inference analysis, we just did it for some particular locations, but in order to extract the actual causal links to this PN 2.5 at high resolution, we have to expand this analysis to other locations. And well, this is everything that we wanted to say. Sorry for the technical problems, and thank you for your attention.
Thank you very much, Kevin, and the rest of the team. Very nice presentation. And as I said, if someone from the audience needs or would like to raise any question to the teams, please use the Q&A section on Zoom and type your question, and at the end of the presentations, we can address these questions. And now is the turn of the second project in this afternoon is weather energy analysis of visualizations for streams on thunders or storms as we have. This project is developing an interactive platform to analyze how extreme weather impacts energy systems. So the team behind this project is Stella and Clement. The floor is yours. When you're ready, please share your insights with us.
Yes, thank you, Esperanza. So I'm going to present what we're doing within the WEAVE project, which is led by myself, who I am a postdoc from the University of Oxford, and Clément Devenay, my colleague, who is a freelance climate service provider. We are mentored by a few people, and they have been very available and helpful, so thanks to them. I wanted to give you a bit of context about why we are developing this project. So it's important to know that energy systems are sensitive to the weather because on the one side, demand depends on the weather, especially the temperature because of heating and cooling in particular. On the other hand, production also depends on the weather, especially renewable electricity production with things like solar, photovoltaic, wind, and hydro. And it's increasingly sensitive to the weather in the context of energy transition for two reasons. First, we are electrifying more and more systems, in particular heating systems and vehicles, which means more weather-dependent demand. On the other hand, we are increasing the share of renewable energy in the European energy mix. So the system is becoming more and more weather-dependent. And as you probably know, the weather is changing with climate change, especially the extreme events. So the challenge as it was posed was to contribute to addressing critical challenges impacting the European power system driven by extreme climate events by developing a visual tool to identify and analyze problematic events using historical data and future climate scenarios. The challenge is in particular based on a database that's called PECD 4.2 for a pan-European climate database. This database contains climate and renewable energy variables for historical and future scenarios. So we have ERA5 for the historical and 6 models with 4 scenarios from CMIP6 for the future. And we have a number of climate and energy variables available. And it's all available on the Climate Data Store if you're ever interested in that data set. The solution we proposed to the challenge, which is called WEAVE, is a Jupyter Notebook-based interactive visualization platform for extreme compound weather and energy events based on the PECD 4.2 data. So in the proposal, we had this figure, this mock-up of what we want our platform to look like. We're not quite there, but we're getting there. So the idea is to have a platform where the users can select a number of parameters about the events they want to study, and then they get graphics that help them analyze the events that they are worried about. So to illustrate what we can do with our platform, I'm going to show an example. In the French electricity system, as an example, one of the most stressful events is when we have a cold wave, which means high demand for heating, associated with low renewable production. So in my example, I'm going to show events where the daily mean temperature is below 5 degrees Celsius in France, and daily mean solar photovoltaic charge factor is below 5%. So we're basically not producing any photovoltaic electricity. Just bear in mind that what I'm going to show, the point is not for you to take the results as they are, but to illustrate what we can do with the platform. Of course, there's more interpretation to be aware of. So for that example, we can first look at the number of events that happen where we have cold temperatures and low photovoltaic production. On this graph, I show first the number of climate events, so when it's only cold, number of energy events, so when it's only not producing solar, and the number of compound events when both events happen at the same time. The x-axis is time, and you have in black the historical scenario, and in different colors the different future scenarios. And the faint lines represent the individual models, and for each scenario I show the multimodal mean. So in terms of climate events, we see that the warmer the scenario, the lesser cold event we observe, which is what we expected because climate change means warming mainly. On the other hand, we see that the solar photovoltaic production seems insensitive to climate in the sense that it's not evolving with time nor with the scenario. You can see that there's a lot of intermodal spread, so there's more to be said, but for any of the models, there's no significant trend anyway. But when we compound these two events, we see, again, less compound events in the warm scenarios, with about half as many events in the end of the century compared to the beginning of the century, if we take the warmest scenario, for example. What's also important for the energy providers is the duration of the events, because they can usually cope with short, stressful events, but if the event starts to be long, then they are out of reserves. So on this graph, I show histograms of the duration, again, of the climate, energy, and compound events. And the vertical lines over here show the mean duration of the events in each scenario. So on the top, you can see the duration of the cold waves, and historical, as we can see, it's about 6 days. But the warmer the scenario gets, the shorter the cold waves become, up to about 4 days in the warmest scenario. On the other hand, for the PV generation, we have mainly a difference between historical and future, but all the scenarios stick together. So is it that these events are shorter, or maybe a bit of model bias here? It's unclear. And once we compound the events, then we see that they are shorter, whatever the scenario, about 1 day less. The last thing we might want to look at with respect to these events is when do they happen in the year? It's important because depending on when they happen, other energy sources might be more or less available, or over demand might be more or less important. So climate events, namely cold waves. So on this graph, I show that's cyclic around the year, and that's showing the distribution of the number of events per time of the year. So we start in January here on the right, and then we go through February, March, and so on. In black, again, is the historical, and as you can expect, the cold waves happen in winter. In the future scenarios, we see that the cold waves tend to happen less in the early and late part of the season, which again is what we expect. If we look at when the solar production is low, we have this bimodal distribution where production is low through November and from the end of January to the mid-February. So the compound events tend to happen during December and January, and we have a slight change with scenario, but honestly not very significant, where we do see less events in the early part of the season and more at the end of December. But again, I'm not saying all that so that you take away information about seasonality of that particular event, but to show what we can do with the platform we are developing, which is select a type of event and see some statistics and explore the database is for Europe, so you can also change countries, and what is stressful for the energy system might be dependent on the country or even on the links between countries. So to summarize the current status and the next steps of our project, we now have a notebook that's shown on the right, so it doesn't quite look like the mockup yet, but it's on its way. With a backend package that are developed and functional, including loading the data, identifying the events and the visuals. And we had to do quite some optimization of the data loading and the event identification so that the whole analysis currently take about 15 seconds. We do still need to improve the graphical representations, and we're getting a lot of help from our mentors about what they need and what they like to see. And also to make once we converge on that, to make the platform interactive, to be more user-friendly. Thank you for your attention.
Thank you. Thank you very much, Stella. Very nice presentation. So if someone would like to ask a question to Stella and to Clement, please use the chat to type your questions. I think Noemi has a questions, but if you don't mind, we address it at the end of the presentation. So now we are very pleased to present the third project, is MLCosting. This project aims to improve the efficiency of the request in the ECMWF data store service. With us, we have the team formed by, sorry about my pronunciation, Duxin, Kubit, Hogan, Nathbin, and Hagen. Please, the floor is yours when you're ready.
Okay, thank you for your presentation, for the introduction. So now let me share my screen. Yes, this one, okay. All right. Okay, so Ming, are you ready? Can you start?
I will go first.
Okay.
Okay. Thank you very much for. So we are a team of 5 people. Think Việt, Minh, Yến, and Hoàng Anh. And we try to tackle a challenge 20. So our project is mentored by Mr. Pitch, Kovin Petrus Kobazan, Gionanta Biavati, and Angelo Lopez Alos. So could you for the next slide?
Yep.
So short is for the problem description. So if you already interacted with the data portal of ECMWF, you just go there and you fill out some form for the data request, such as the date range and spatial range and some variable you want to include in your data set, and you send the request to the system. It's very simple for user. However, from the server side, it becomes difficult if we receive like hundreds of requests at the same time. So it is difficult to for the resource allocation. So for that, it would be beneficial if they have a rough estimation of how each request gonna be processed, and that is where. However, with the current system, with the current rule-based system of the ECMWF, probably is not gonna produce a good result. So that's why we produce a project to improve the current system. So in general, we are provided with a large data set from the historical request to ECMWF and the corresponding duration of each request. And so we're gonna train on this data set to give a rough estimation for each request. For an important note on this one is that we only use the request from the user to make the estimation, and there's no feature from the server side, so we don't know how busy the system, but we only use the request submitted by the users. We feed the data to a machine learning model. Here we used XGBoost regressor with hyperparameter tuning, and this system after training can be used for real-time prediction. So next, my colleague will now present the technical architecture for the solution.
Yeah, thank you, Viet. So to continue, our solution consists of 4 layers. So first layer is a schema handler. So schema here is the available choice for each dataset that we can choose which part of the dataset that we want to download. So the schema handler will firstly auto-fetch the schemas from the 3 data repository, and then we will transform the data request into the standard form for each schema. So for the next step, the second layer will be the feature engineering. So in this step, we will transform the data request in the standard form for the last step into the encoding vectors. So for the method for encoding, we have multiple encoding pipeline. We have multi-label binarization for categorical arrays. We'll have one hot encoding for single category, and we have numerical array handling with shape validation. And after this step, we have the encoding vector for each data request. So the next step will be for the model for the training. So we call it machine learning pipeline. So for this step, we use XGBoost method to train the data. So we use XGBoost with the hyperparameter optimization. And then for the last step would be the API layer. We use a fast API to trigger and to show the transformation, to show the data transformation and the prediction method in an endpoint. So we do the step. Yeah. So here the technical challenge that we have addressed. For the feature engineering challenge, we have built a sophisticated multi-type encoding pipeline for diverse data type. And we have automated the categorical encoding we have multiple method process multiple methods. And then for the hyperparameter tuning challenge, we have optimized XGBoost parameters using up to now is a Python package across multiple datasets, and then we have balanced the model complexity with the generation's performance. And for the evaluation framework, we have developed quantitative metrics, which we use MAE, RMSE, and MAPE for model comparison. And we have created quantitative analysis tools. So we have plots, and we have we have residual plots and feature importance plot. Next, please. Yeah. So here is an example of a request. So we see that this is a data request from the CAM European Air Quality Analysis dataset. So from this request, our model had to predict that the system of the center take how many time to gather all the data that the user choice here, and then get it ready for the user to download it. Yeah, next please. Yeah, so I think we will present our preliminary results.
Okay, thank you, Minh and Viet. And so now I will present some of our preliminary results. So first we come to the quantitative results. We have validated our model, our machine learning models on 4 data sets majorly, and we use three error matrix: the mean absolute error, root mean square error, and mean absolute percentage error. So for the first 2 matrix, they are in order of seconds. So you can see the root mean square error is quite sensitive to the to the large arrows, large normal arrows. So as you can see that for root mean square error, they are sometimes several times higher than the mean absolute errors, and they are quite normal in this kind of data set. And we also plot the results. So first we plot the residual results of the AR5 pressure levels, which is one of the data set with the highest requests, the highest numbers of requests. So we have on the x-axis actual duration, y-axis the predicted durations, and they are all in the log scale, right? And so you can see that the red line is the perfect prediction, and so our predictions looks quite close to the red line, except that we still have some points over there because the actual duration is faster than the prediction duration, and it could be because of the multiple caching layer in this system, so that it's not just about the request parameters key who counts, but also maybe there are some like behaviors in the system that accelerate the actual duration. So that's why we have some points over there, right? And another data set, the ER5 length, and we still have same kind of behavior with a more significant amount of points over there, which indicates the multiple caching layer that's issue, as I said. And the projection CMIF6, because so in this data set we have less point of samples, so the R square is relatively is very low, but still if you look at the results, they are not they're still quite decent, right? And the kind of Europe air quality, and for this data you can see that they are kind of they form kind of clusters of requests with fast duration, with fast processing request medium, and the high and the high load request, right? Okay, and so for the next steps, and we have a project. First, we have to improve our either our machine learning models or our feature engineering pipeline to improve the final results. And so, speak of the final results, we have to also establish a kind of a new meaningful matrix who can like show exactly what is the tolerance of the arrows. And so also we have to finish the API endpoints development, and to deliver the final product with complete API endpoints. So thank you for your attention, and this is the end of my presentation. If you have any questions, don't hesitate.
Thank you very much, MLCosting. If someone has any any questions, please type in the questions section, and we will address at the end of the talks. Thank you, very nice. Now we have the next project with us is EVALKIT, Model Error Detective. Is behind this project. There are Nadia and Zakaria as developers, and they are creating Jupyter notebooks to analyze forecast errors and extreme events. So the floor is yours.
Thank you, Esperanza. I will share my screen. Okay, so you can see my screen?
Yes.
Okay. So good afternoon, everyone. My name is Nadia, and I'm here with my colleague Zakaria to present EVALKIT, our model error detective, which is developed for Code for Earth Challenge 30. And before I start, I would like to thank our mentors for their support and guidance throughout the past months and like for the remaining months in advance. So let me start with a reality check. So weather forecasting systems are incredibly sophisticated. Like while weather forecasting are evolving, but the diagnostic and evaluation tools are still stuck a little bit in the past. So till now we have fragmented and like model-specific tools that are used by scientists, each one in its part, and we don't have a systematic and a comprehensive and like a common approach that can be used with all models and like with all people by all scientists. In addition to that, one other limitation is that the current ECMWF plotting tools can only plot the last few days. So essentially, we are flying blind, like when it comes to long performance analysis tools. So here comes EVALKit to provide a unified tool in order to assess and evaluate surface variables from models within the same framework. So our goals are threefold. So first, of course, we will start by building this unified diagnostic tool to analyze extreme events from both physics-based models and AI-based models. And this framework will be in a suite of Jupyter notebooks organized through the different components that we will present later and distributed in GitHub for further and continuous developments, so even after the Code for Earth project. And lastly, we are trying to leverage as much as possible EarthKit's capabilities and only use other libraries when the functionality that we want to implement is not available yet in EarthKit. So our goldmine data is a Mars archive system, which has meteorological data, reanalysis products, and operational forecasts, all organized and categorized in the same interface. So we are working with surface variable forecasts, mainly precipitation, wind speed, wind gusts, and temperature. So this data is the input of our two core components that we implemented till now. The first one is dynamic weather mapping visualization tool. So till now, the scientists had only used static maps. So now we will provide a notebook which has interactive maps in which the user can either retrieve or read a local grep file and display the surface variable in the map. The user can zoom, can hover, can pan to see the values. You can even see the evolution through time in the map. And the second core component is the clickable time series. So this one, it takes the first one a little bit further. In this one, the user can load one model or two models. And then when he clicks on the map, he can plot the time series to see the evolution through time. And if observations are available, he can also overlay them with the existing forecast models. And this way, he can assess the accuracy of the forecast models by comparing them with the observation models. So now I will let my colleague present the graphical visualization of both components.
Thank you, Nadia. Can you just pass to the next slide, please? Yes, as my colleague has just explained, it's about creating some notebooks in order to facilitate the creation of dynamic mapping and visualization or time series visualization. Our first tool is the dynamic weather mapping visualization, which is based on three components. The first one is to provide the ability to the user to retrieve the data from a user interface by configuring several parameters that can extract to retrieve the data from Mars archive. The second part is the variable calculation. We will provide for the user the possibility of calculate, for example, accumulated precipitation or wind speed based on the new UNV parameters, and also to provide to calculate the estimation of maximum or the minimum. The third part mainly is about plotting interface, where the user can plot the results based on three type of plotting. The first one is the the dynamic map where the user can have the ability of interactive with the map, which can visualize, for example, pixels values. And the second one is mainly for static maps, which is based on EVALKIT plots for the moment, which the user can use it in the reports, something like that. The third one is the multi-steps visualization, where the user can see the different changes over the time for its rasters. Yeah, this is the first one for interactive map. Here we can see, for example, the user can have the ability to interact with the map based on, for example, like extracting the values of the pixels, visualizing it. The second one is based on static map, based on EVALKIT plots. And the last one can just, yeah. We can here see the dynamic and the change visualization of the type for the multi-steps configured by the user. Thank you. Next one is the interactive time series analysis tools, which we can extract from by the user to extract time series and visualize them with an interactive way. The first step is like always is retrieving the data and how to configure parameters and analysis control. For example, if you want to plot time series of also of surface variables, wind speed, and how to calculate wind speed also. And also we can provide for the user the possibility of the accumulation, for example, for one of the variables, like for precipitation. And we can also overlap this with some observation data, so the user can compare the models. For example, if we have IFS or EFS models with observations data. Yes, here is an example. For example, here the user can click on multiple points on the map and show the time series for each point. Yeah, for the here also we have an example of the overlap of observations with the prediction models. Yeah, for the next step, what we still to do is to have the ensemble forecast tools. We want to analyze the probabilistic do the probabilistic analyze in order to quantify the forecast uncertainty, like by giving the ability to the user in order to create some visualizations like metrograms and cumulative distribution functions and plumes for the ensemble forecast members, in order to make the user let the user the possibility of quantify its the uncertainty. I think thank you for your attention. You have any comment or any question we place to answer this? Thank you so much.
Thank you very much. Impressive, very nice. So as you said, if someone has a question for this EVALKIT project, please type the questions on the Q&A box. And now the last but not least project, PACE, Physics Aware Consistency Evaluator. This project is developing a tool to check how realistic AI models are for weather forecast. So we have the developers behind these projects are Peter, Martin, Marek, and Martin. The floor is yours, please, when you're ready. Yes.
Yeah, thank you for the introduction, Esperanza. And hello everyone, I'm Peter and I will be presenting our project PACE, which is Physics Aware Consistency Evaluator, where we evaluate physical consistency in machine learning models. So why physical consistency matters? So machine learning is being increasingly used in meteorology due to its computational efficiency and ability to learn complex patterns. And these models often show great skills and even outperform traditional models in some cases. For example, in statistical scores such as RMSE or correlation. However, one of the key challenges remains that these models represent well physical processes in atmosphere. So, for example, machine learning model might predict wind fields which are not consistent with pressure fields, and thus breaking a geostrophic balance. And so our goal is to address this issue by developing a physical consistency evaluation framework. And so this framework will consist of different diagnostic checks. We will look at the geostrophic balance, hydrostatic balance, some statistical checks such as cross-variable correlations and spectral power analysis, then mass conservation, energy conservation, and then at the end we will conduct case studies where we will analyze cold and warm fronts as well as convective events. So here is the first diagnostic, the geostrophic balance. We obtain the geostrophic wind by computing it from pressure and wind fields. Then we also compute the ageostrophic wind, which is the difference between actual wind and geostrophic wind. And then we can plot the ratio of these two. So the small ratio values typically indicate the strong geostrophic balance, and the high ratio values are found in the frontal or convection regions, but also may indicate some physical inconsistency. Now, if we plot this ratio on vertical pressure levels, we can indeed see that in mid-altitudes, the ratio is quite small, which suggests that the geostrophic balance holds well. And if we compare the different lead times for the GaussCast output, we can see that the ratio is actually increasing, which suggests that the geostrophic balance doesn't hold well in the higher lead times. Now we have a look at the hydrostatic balance. We compute this by looking at the geopotential difference between adjacent pressure levels. First, we compute it from the temperature and humidity fields, and then we also compare it with actual geopotential difference that the machine learning model output predicts. And then we can compare this by measuring the absolute error. So typically in the tropics, the error is high due to convection, which breaks the hydrostatic balance. So now we again have a look at the vertical profiles of absolute error as well as relative error. So similarly to the geostrophic balance, we can see that the hydrostatic balance holds well in the mid-altitudes around 500 hectopascals. And with the increasing lead time, the hydrostatic balance doesn't hold that well. Now I will hand over to Martin, who will present the statistical correlations as well as the framework design.
Yeah, okay, so thank you. Okay, so cross-variable correlation is also one of the basic inspection diagnostics we can perform. So here is a simple example of sample-wise aggregated correlation. So from each sample, a correlation between a pair of variables is computed. Those outputs are aggregated over the dataset, and then we have a mean correlation and standard deviation, which is basically standard deviation in temporal variance. Here, we plan to extend this to a more in-depth spatial analysis of the correlation coefficient, and also provide a direct comparison with a reference dataset if such is available. Next, please. Also, we can aggregate bivariate histograms for specified pairs of variables and then visualize that as bivariate histograms. And then we can, again, compare with a reference dataset or check if it changes with lead time or if there are any changes during special events. Okay, next, please. Okay, so here is a brief scheme of the workflow when working with PACE. So basically, the user specifies the run or the setup in a config file where you specify the dataset, the metrics you would like to evaluate or the diagnostics, and then you can specify also a temporal or spatial slice that you would like to focus on, optimizing the data loading before the computation of the diagnostics is performed. Also, you can switch which diagnostics you would like to visualize using the inbuilt methods. And additionally, you can extend this to your own dataset if you follow the loading logic. Also, you can implement your own diagnostic tools within the framework based on the examples provided, as well as additional post-processing routines. So the basic idea is that it is implemented in PyTorch, which is kind of unusual because a lot of things needed to be implemented from scratch, but it provides a few advantages. One of which is that it can be used as a soft constraint in the model training themselves as a form of physical regularization, meaning that the diagnostics, if formulated that they serve as a loss function, can enforce the model to follow the constraints. Also, it can be used to diagnose potential errors and their source, most importantly, using tools such as GraphCam and similar, which can make the models more explainable and potentially improve their development. Next, please. So in conclusion, the challenge addresses a key gap in the evaluating physical consistency in either machine learning-based weather forecasts or downscaling products or similar MLWP products. And we plan to complete the implementation of the diagnostics as listed in the previous slides, perform the case study analysis for some selected events, either in the GraphCast dataset or for CorDiff, which is more high resolution. Also, we still need to do some structural code cleanup, meaning improve logging and browsing of outputs, and extend framework to support more outputs and datasets. So that is all from our side, and thank you for your attention.
Thank you very much to you for the presentation. Very well done. So now I hand over to Tina, just in case there are any questions to address.
Yes. 1 second. Yeah. So are you seeing my screen now? The presentation?
Yes, you need to put a presentation mode.
Okay. Yeah, okay, that was really an interesting session, a lot of interesting presentations, but a shout out to the audience. No questions? Really? We had a lot of questions in the last webinar, so yeah, I'm looking around. Oh, there's something in the chat. All right. Okay. So there was a question, but the speaker has answered the question already. Okay, you still have time to post your questions while I go, you know, kind of wrapping up the session as well as what to expect next. So we are still 1 month or 6 weeks to go, or 5 weeks to go with the coding phase. So what you saw right now is where the teams are at the moment. Some of them presented, also most of them presented what are the next steps. And if this really raised your interest, you're curious, then we would like to invite you for the last phase of the program, which is the final Code for Earth Day. And that will take place in Bonn on the 25th of September. But so we are streaming the event online. So if you're an external person and you're not involved in Code for Earth directly, so we welcome you to join us online on the 25th of September. The agenda will be out soon, and also the registration, so that you can register and we can provide you with more detail in time. Looking now again to the Q&As. I don't see any. Cannot see it. There's a simple question for the AI for air quality team. Giuseppe Carlino writes, I missed what the team is using for ground truth benchmark. And are you also comparing the AI results with measurement stations? Let me put this in the chat to everyone. So anyone from...
I may answer that question. Can you hear me?
Yes.
Yes.
If there is any other shortage. Okay, so for the ground truth, we are using the PM 2.5 at high resolution, okay, from this CAMS Europe product. This is what we are using to train the model, okay, and we are evaluating like as usual, like dividing by different data sets, test, validation, and train. And also, part of what we want to do next is to evaluate against the real observations, from measurement stations in Europe, and then also outside Europe. That will be.
Good. Thank you. Any more questions? No? Then I would like to have another round of applause for all the teams. Thank you for your interesting insights and to get an understanding where you are. We really appreciate your efforts, and it's really nice to see how the project's evolved over the last couple of weeks. And with that, yeah, thanks again. Thanks for the audience and for joining the session, the midterm webinar, and looking forward to see you all end of September. Have a nice summer and take care. Thank you. Bye-bye.
Thank you.
Thanks,
Bye-bye.
everyone. Bye.
Bye.
Bye.